Alright, so I'm going to start by talking about anaerobic glycolysis, the first stage. And we'll start with a glucose molecule, which will be broken down through phosphorylation by hexokinase. Which will be brought through by bringing in an ATP here, which will lead to your GP6, or I'm sorry, G6P, glucose 6-phosphate. Which will go through isomerization with phosphoglucose isomerase, your PGI. And this will lead you to F6P, your fructo 6-phosphate, which would again go through phosphorylation let's get a clearer picture there. By bringing in an ATP again. Alright. And this is actually where your rate limiting enzyme, PFK, phosphofructokinase, which will be basically the reason for the speed of the reaction. So how fast this process is going to be able to go is going to be dependent upon this phosphofructokinase. Enzyme could be increased by ATP concentrations being low, and then it gives and ADP concentrations being high. It'll give the rate limiting enzyme kind of a boost, and more PFK is going to be involved, which would then increase the rate of this reaction process. So from the fructose 6-phosphate, we'd be brought down to a fructo bisphosphate, by aldolase, sorry. I'm sorry, that'll be brought down through by the PFK through the phosphorylation, and then the aldolase is going to bring this here to either your GAP or your DHAP with phosphate here. And then that process will lead us into the stage 2 of the anaerobic glycolysis. Well, here I'm going to continue with the anaerobic glycolysis, starting the second stage, where we have the gap in your DAP here, which can go back and forth because of this enzyme TIM here, triose phosphate isomers. From here, we would have the enzyme GAPDH, your glyceroldihyde phosphate dehydrogenase, which will bring us down to bisphosphoglycerate BP6, because of, see that here, because of NAD coming out into NADH. So because of the dehydrogenase here, we're going to be taking out that hydrogen from your NAD, and it will give us the bisphosphoglycerate here, which will be brought down to, after adding an ADP, will give us 3 phosphoglycerate, your 3p6 from your your PGK up here, your phosphoglycerate kinase, and then we have PGM here, your phosphoglycerate mutase, that is going to bring us all the way down to 2 phosphoglycerate. P2PG. And then to further break down our phosphate groups here, we will bring in enolase, enzyme enolase, Mg2+, which will bring us to phosphophenyl pyruvate, or your PEP, and then also taking out some H2O here, and then ADP, bring it back out to ATP this time, to give us our pyruvate from pyruvate kinase. So again, breaking down another phosphate group here with the kinase, and then that's going to give us the ADP to ATP and leave us here with pyruvate as our ending enzyme, our products being our pyruvate and 2-ATP. Alright, so here we have the Krebs cycle, which will start off with the pyruvate from the glycolysis. And pyruvate will be broken down into acetyl CoA, and this will be done by bringing in an NAD plus and getting out an NADH, as well as taking out a carbon dioxide molecule from the reaction. This will give us the acetyl CoA, which will start the process beginning with citrate synthase. So the synthase is basically saying that it's creating your citrate here, which is going to be the start of the process. Moving on next to the enzyme aconitase, leading to your isocitrate. and then your isocitrate is going to be broken down with your NAD plus, again taking out a hydrogen here, so you have NADH plus H, sorry, and a carbon dioxide coming out of here as well. With the enzyme making this possible being your isocitrate dehydrogenase, which your dehydrogenase is again going to be saying that it's removing the hydrogen here. This is also actually the rate limiting enzyme for these chemical reactions in the Krebs cycle. So throughout this process, the rate limiting enzyme is going to be the isocitrate dehydrogenase. This is going to be basically the determinant for how fast or how slow the two carbons are going to be removed from the beginning citrate from the acetyl-CoA. So how fast are those two carbons going to be removed, and these chemical processes going to be conducted through this part of the Krebs cycle. And then from here we will end up with your alpha. So here we got after that, and then we got alpha or keto glutarate, which is broken down from alpha glutarate, keto glutarate, sorry, dehydrogenase. Again, where we will have NAD plus the H being removed here and a carbon dioxide. So we end up breaking down. Now we have both of the carbons being removed, and we're back down to 4, which will continue through the rest of the process here. And this is going to take us down to our succinyl-CoA, and that was brought on by your CoA synthase, or also where your GTP in this little diagram here, where you have your GDP and P coming out to give you your GTP, and your ADP into ATP to make that possible. And this will give us that GTP at the end of the cycle, which in turn goes into your ATP, being one of your end products. This will move on further to be succinate, and then that enzyme dehydrogenase here, succinate dehydrogenase, is going to come in with FAD this time, and FADH, still taking out that hydrogen from your FAD here, and this is going to form your fumarate, broken down from fumarase enzyme to create just a little chemical, some chemical changes to give you the L-malate from your fumarate, which will then be broken down by the malate dehydrogenase with an NAD plus to NAD H. So taking out that H again, and then leaving us with the oxaloacetate as the end product. And then from here, really we just add up all of our products. So we have the 3 NADHs and the F1FADH and your GTP, and it'll give us an ATP. Each one of these is going to be 1.5, and then we have 3 of those, which is going to give us 2.5 each time. What I'm going to do is the Krebs cycles ran 2 turns through the cycle, and you add all those up, and in turn, usually one glucose molecule is going to give you 30 ATP total. But that wraps up the Krebs cycle. One last thing I forgot to mention was the other rate limiting enzyme, which is going to be your cytochrome oxidate, or COX, which is basically going to be your other rate limiting enzyme in the Krebs cycle, basically the overall rate limiting enzyme altogether after you get your products, how fast they're broken down into the ATP.